distributed pervasive systems. We're going to talk a little bit about the history behind pervasive system, not quite the history, but how they evolved. We'll talk about sensor networks and sensor platform issues as a underlying theme behind pervasive systems. We're going to say a little bit about energy issues in the context of green computing, and then we'll look at a case study of smart buildings as both an example of a distributed pervasive system and a green computing system. Okay, I'm going to do a wrap up. So, back in the very first class when I was talking about distributed system history, if you remember, or maybe you don't remember now, I said as systems have evolved, computing has gotten cheaper, smaller, so now it is possible to embed computing into lots of other devices rather than treating computing devices as standalone devices. And this has given rise to what is referred to as pervasive or ubiquitous computing, which essentially means that there's computing everywhere in our environment. And as a result of this, you hear about these terms called smart cities, smart homes, smart highways, smart classrooms, and so on. So here are many examples. So this is an example of a dashboard with a computing device embedded into it. You can connect your phone to it, it can run apps and so on. This is a smart entertainment system. It's an internet-connected television. There's a washing machine that is connected through the internet. You can control it with your phone. This, I think, is not very visible. That's an example of a smart city, or rather a smart highway, where the road interacts with the car and alerts the driver if the conditions are slippery, because there are sensors that indicate there is ice on the road, and you get an alert saying you should drive more carefully and so on. So everything is becoming smart, maybe except for humans. That's the only problem right now, but leaving that aside. So all of these smart devices are also referred to as Internet of Things. That's another term that you hear. And this is basically saying you take these devices that are individual. So what I showed you here are individual devices that may be internet enabled, connected, have computing in them, and you connect them all together, and then you get the Internet of Things. Internet of Things essentially says what happens when you connect things of any sort, whether they are cars or devices or appliances, to the internet, and they are all able to communicate with one another, and you can control it. Okay, so that's basically the same thing what I mentioned on the last slide, except for devices being networked together. Okay? Another way to look at it in the computer science terminology, this is also referred to as a sensor network, a network of sensors. Okay? So you can have lots of these sensors embedded in the environment and network. And the question is, what are some of the issues that arise when you design a distributed system of that sort? That's really what we want to focus. Okay, it's driven by the miniaturization of computing. Computing devices are becoming smaller and smaller. These sensor networks of these smart devices are at one extreme, where they are very tiny embedded microcontrollers and small radios that enable them to communicate with one another and so on. So what we will do is to look at how to design the systems, but I'll talk about a few other applications before we do that. This is just taking some of those smart applications that I talked about in the very first slide. Here is an example of devices you can buy today for smart home. Here's a light bulb that you can is connected to your wireless network. You can turn it on and off. You can change its color and so on. Here's a smart outlet that you can plug into and you can control remotely. It has an ability to communicate, and you can turn it on and off. You can get a garage door opener that is similarly controlled remotely. This is an example of a smart thermostat. It employs machine learning algorithms to learn when somebody is home, when somebody is not home. It can turn your AC and heat on and off automatically. So you don't have to control it to tell it I'm going to leave the home, so turn it down. It has occupancy sensors, and it learns your habits and is able to then automatically control your air conditioning and heating system. Okay? So these are some of the examples of devices that you can buy for home environments. There are similarly slew of devices that are now becoming available for personal health monitoring. Okay? So here is a whole class of these devices that are driven by this fitness or they refer to as fitness or activity trackers. They track how many steps you take, how much you run, how many stairs you climb. They can even track blood pressure and other things. So I have one of these devices. I think I showed that in the very first class. So it has a tiny microcontroller and a Bluetooth radio, okay, that enables it to take whatever data it's collecting and connect to the internet and upload it. So typically use a phone to connect to it. Okay. Here's an example of a weighing scale that has Wi-Fi capability, so it can keep track of how your weight changes over time. It can even recognize different people based on their weight and so on. Okay. And then, so these are just the fitness stuff. There are lots of these devices or sensors available to track people with diseases and things like that. So diabetes is a good example where there are trackers that track blood sugar for people who have diabetes, and they can alert you to take medication and so on. Google has actually come up with a smart contact lens that you wear in your eye. It has a tiny sensor and it actually tracks your blood sugar based on whatever it can see within your on your eye, for example, and it can upload that to a server. So there are all these examples of sensors and devices that can do a variety of interesting things. Yeah. Now the typical architecture, so there are different kinds of architectures for sensor network, but there are two that are very common. Lot of these personal devices that I showed you in the previous slide, what they do is they have sensors and they have small wireless radios. Typically the radio connects to an intermediate device like a cell phone, okay? And it communicates with the cell phone, it uploads the data to a phone, and then the phone will then upload it somewhere else where it is stored and archived for long periods of time. Okay? So you have a low power communication to an intermediate device. Typically this is a phone, but it could be a small gateway device that you put somewhere. Okay? And then you communicate with that intermediate device. That intermediate device is connected to a network or the internet, and it will upload to the server or do whatever it needs to do. Okay? Another architecture is your collection of these sensors. They may be directly enabled, internet enabled. Okay? They have direct connectivity. So they don't need an intermediate device. They can directly upload the data to a server. Okay? That's the other architecture. There's a third architecture where sensors actually communicate with one another, route data to a network to an intermediate gateway, okay? And then the gateway uploads. That is somewhere between this and this, where in some of the sensors have internet connectivity, others don't, or there's a gateway that has internet connectivity. Sensors will relay data through other sensors to a gateway device or a node or sensor that itself has network connectivity, and then upload it. Okay? So these are various network architectures you have. But in the end, the data is stored on some server machine where it can be archived for long periods of time, and you do interesting things with it. You can process it, you can provide some recommendation, you can use it to provide control. Okay, that's another important thing, where you get data, you process it in real time, and you exercise some control over some device, okay, like an air conditioner or a heater, as I was talking about. Those are some of the examples. Okay, so this is typical architecture of these applications. Now we'll talk a little bit about each of these devices, what they contain. Okay? So you should think of each of these smart devices as some sort of a sensor platform. Okay? They can be also thought of as a highly resource constrained distributed system. Okay? So far we have looked at client server architectures and so on, and machines are not resource constrained. So here we are going to be actually at one extreme where they are highly resource constrained. So what code they can run, how much memory and storage they have is actually orders of magnitude less than typical machines. So some of the design considerations are going to be very different. So we'll look at this in a little more detail, but you will see that they're very small CPUs, 8-bit architectures, not 32, not 64-bit, tiny microcontrollers, low power network capability, okay, low bandwidth, tens of kilobits per second or hundreds of kilobits per second, not megabits or gigabits. Okay? Small amount of local storage. Okay? Just when they are not connected, they can store data locally. Okay? You don't have large disks and things like that, but you may have small amount of flash storage. They of course have the sensors that do the sensing. And last but not least, typically most of these nodes are battery powered. Okay? That brings a new dimension to the picture, because even if they were more capable, since the battery that they have is tiny, if you use up all the battery, the device becomes inoperable. So battery life being more energy efficient is a very important design constraint. So they're not only resource constraint, they're energy constraint. Okay? That's the thing to keep in mind. So we'll see a little bit about each of these things now. So here's an example of a CPU. I'm not going to go into a lot of detail here. There are different classes of microcontrollers you can get. At one end, your 8-bit microcontroller, there are 4 kilobytes of RAM. Okay, that's kilobytes of RAM, not megabits or gigabytes of RAM. So very tiny amount of memory. So if you write a program to run on the sensor, the whole program and the OS has to fit in 4 kilobytes. Okay? Very different kind of design consideration. You can't just write code without thinking about its footprint. Typically when you write code, you don't think about how much RAM is it going to take or anything like that. You just write it the way you want to write it. Here you have to write it so that it actually can even fit in RAM, otherwise your application will not even run. Okay? It has, it runs at only megahertz, not gigahertz, so it's much smaller or lower clock speed CPU, so you can't run very compute intensive applications on it and so on. You of course have more capable processors, but they're never going to be as capable as desktop class or server class. So this is an example of an ARM processor that some of the more capable sensors will run. Okay? Even phones have ARM processors. So they are an example of more capable node, okay? But they will typically consume a lot more power. So either they need more battery or they have to be somehow plugged in. For those environments, these kinds of microprocessors will work. But for very small sensors, you are actually stuck with very low-end processors. Okay? 8-bit architecture, very small amounts of RAM and so on. Now, as far as communication goes, most of these sensor devices tend to be wireless. They use some sort of wireless communication. There's an entire class of wireless radios that you can buy. Depends on what is the application. So you can buy put a standard Bluetooth radio on your sensor. There's a class of radios called Zigbee that has become very popular. Okay? It is not the same as Bluetooth, but an analogous type of wireless standard, lower bandwidth than Wi-Fi. Wi-Fi radios are much more power hungry. So if you put a Wi-Fi chip on your device, it is going to consume a huge amount of power as compared to some of these low power radios, and your battery life will be significantly reduced. Okay? As a result, using lower power radios allows you to take a tiny battery and have it last for longer periods of time. Okay? So since energy is an important constraint, what kind of communication technology you use also becomes important. So most of these would either use Bluetooth or Zigbee. Yeah, that's very common. There are other radios you can buy that are not standardized, but you can put them for specialized applications. Yeah. But the the key point is low power, lower range, lower bandwidth. Low power also means the range is going to be small. Okay, if you cannot transmit at high power, you can't transmit for longer period of distances. So rather than having several thousand feet, you may be in tens or hundreds of feet radius, for instance. Okay? And the bandwidth will also be lower. You will be in the hundreds of kilobits per second bandwidth. And most of these devices will have some form of storage. Okay? You can't put a big disk drive onto a tiny sensor. Okay? You have to use other forms of storage. So most of these computing devices will have flash storage. Okay? Same kind of things, you put the flash chips you can put in a camera or things like this or your phone. Same kind of flash storage is typically installed in these devices. Flash is not very expensive, so you can actually put hundreds of megabytes of flash easily, or even gigabytes of flash onto a device. Okay? So storage typically is not as big a bottleneck. You don't get a terabyte storage, but a tiny sensor that's recording some data, if you put several hundred megabytes or a gigabyte, that's enough data, enough storage to log, let's say, for several months at a time without any problem. So typically they are memory constrained, compute constrained, communication constrained. Storage is not as big a deal, okay, relative to the other things. You can easily put storage like NAND flashes. These are technologies of flash storage, NOR flash and NAND flash, and that's a removable flash media. It's the same kind of device. And they are inexpensive, and you can put reasonable amount depending on the application. Okay. But the most important aspect here is batteries. And battery is basically what's going to power these devices, and that becomes a big constraint. Okay. The smaller the battery, the better the packaging. If you put larger batteries, the packaging becomes bulky. Okay? And depending on the size of the battery, you have a certain lifetime. The more compute or communication you do, the more energy the device is going to consume, and the shorter its lifetime will. So most of these devices do several interesting optimizations to conserve energy. One important one is called duty cycling. What duty cycling means is the device sleeps for some period of time, and it wakes up, does some sensing, computing or communication, goes back to sleep. Okay? So most of these battery powered sensors are not always on, unlike a typical distributed system or a server which is going to be on when it's running the application. Here battery constraints force the devices to take naps. Okay? It goes to sleep every so often. So you have to set your duty cycling rate depending on application needs and the battery. The longer you duty cycle, which means the longer you sleep, the more your battery life. But then the shorter the useful things that happen, because you go to sleep for longer periods of time. You wake up, you can do sensing, computing, communication, then you go back to sleep. Right? When you're awake, you do useful things. When you sleep, nothing useful is happening as far as the device. So there are all these design trade-offs. As a system designer, you have to ask, what should the duty cycling rate be? It is not uncommon to see 10% duty cycling when the device is sleeping for 90% of the time. Every minute it wakes up for 6 seconds, does something, goes back to sleep, okay, for the next 54 seconds. And it wakes up again. Okay, that's a 10% duty cycling rate. Okay, so now that is going to limit, if anything interesting is happening during the time you are asleep, the sensor is not doing anything, it's not going to sense. So you will miss it, for example. Okay. So all of these design issues come into play. Now there are other kinds of sensor nodes people are looking at which are battery less. Okay. So what these would do is they have to harvest their own energy. There is no onboard battery. They have to somehow generate their own energy. Right. There are many ways to do this. You can put a tiny solar panel on this device. The devices are fairly tiny, but you can put a very tiny solar panel. It will generate some electricity, okay, even in ambient condition. Of course, if you put it in a dark environment, doesn't help. But you can actually use that and generate some electricity and power the device. Okay? That's one way to do it. There are research projects that are looking at harvesting ambient wireless energy. There are all these Wi-Fi networks that are sending packets back and forth. There is some energy that is being expended in sending this packet. If you simply just listen for these packets, you are getting wireless energy through wireless media. So you can just sit and listen until you have gotten enough energy, then you have enough energy to transmit. So there are people who are simply looking at harvesting ambient wireless transmission that are there everywhere in the environment to do this. Okay. Others have even looked at harvesting vibrations. Okay. So you can actually get a smart switch, a switch that you put on the wall, that every time you switch it on and off, just that motion allows it to harvest a tiny bit of energy. And then you use that to do some transfer. Now if you're actually putting a sensor in the switch, you may as well connect it to AC power. So there is no reason to do this, but there is a project that does try to harvest this kind of vibrations or motion to harvest energy. Others are looked at using wind. Okay, so there are people who have designed sensors that you put in air conditioning ducts, because there is airflow. You can have equivalent of a very micro wind turbine which is going to rotate as the air flows, and then you use that to power the sensor. Okay. So lots of clever techniques to generate your own energy, because battery lives are limited. Okay. If you put 100 sensors in a building, okay, and they have 2-month battery life, every 2 months you have to go and replace 100 batteries. Okay, very painful. Because you have to send some, this has to be done manually, not automatic, right? So this kind of issues do limit the utility of some of these devices. Okay? So that's battery power, which is an important design constraint. And then there are, of course, the sensors themselves. Depending on the application, there will be a whole slew of them. Okay, not every device will have all of these sensors, but you can think of temperature, humidity, vibration, acoustic, light, motion sensor, imaging sensors are, of course, cameras, rain sensors, GPS, location sensors of various sorts, and so on.
So just go back one slide. I don't have a big physics background, so what would happen if you put a bunch of these devices that harness energy close together? So you could, vibration and harnessing devices close together, and then like Wi-Fi harnessing devices close together. Will they affect each other? Or
it depends on what you are trying to harvest. if you're harvesting light, of course, it doesn't matter, right? So you can put them independent of what's happening on other devices. Same is true of, let's say, vibration, because you're actually, what happens is when you move, it is, not when you move, when the device sits on a surface that is vibrating or moving, it is simply harvesting that vibration. Just because you put them next to one another doesn't impact it, it's how much vibration there is. People have developed these sensors for monitoring bridges. Okay? So there are cars and traffic that goes on the bridge, there's a lot of vibration. That vibration has energy in it and you can actually harvest that energy. The proximity of the devices does not in these cases impact how much you can harvest. But that depends on what technology you're using to harvest. If you're harvesting wireless energy and things like that, putting them in places where they have enough energy to harvest is probably as important. Most of these are research projects where they're self-powered sensor, where you don't have commercial products that do it because people are trying to push the boundary on what you can do. The standard off-the-shelf commercial sensors are all battery powered, or they just use AC power. So you can put a variety of different sensors. So you have essentially what is shown here is a computing node. Okay, it runs a tiny operating system. Okay. This is a USB thing that you have to use to load the code. It doesn't do anything else. So now this by itself is not going to do anything. It's a tiny computer. You have to connect a sensor to it, write some code to collect data from the sensors and communicate and so on. Okay. So that's just the platform on which the sensor is going to be housed, and you can plug in whatever sensor you want. Okay. Now that's an off-the-shelf device. If you build your own application, you probably make the whole hardware design yourself, which includes the sensor, the platform, and so on. Okay. These are more general purpose one that you can use, connect any of these sensors and build your own application very quickly without having to prototype hardware. So I already mentioned self-harvesting sensors, which is really pushing the boundary of what you can do, how much energy you can harvest, and how to power these sensors perpetually. Okay. So there are many design issues here, which would be a good topic for a course in pervasive computing, but I thought I should mention some of these things. So we already talked about battery power, so that's some very important design concern as far as single node is concerned. But when you connect network of these, there are other design issues you have to think of. Okay? So inside, so this is a network of sensors. So those are sensors. Typically, there's a gateway, there's a back-end server where the data is archived and so on. Okay? So when you have this network of sensors, you have to think about various issues. Data aggregation is one. Okay? So here you have shown an example where there's one gateway node. There are all these sensors. The sensors have to relay data through other nodes to reach the gateway, because their wireless radio doesn't have a range that is long enough to directly talk to the gateway. So in order to transmit data, they have to actually use other nodes as routers, essentially, that will send the data forward, keep forwarding it until it reaches the gateway node. Okay. So routing, how to do routing in a wireless sensor network is an important problem. Okay. Now as data comes to you from other nodes, how do you take that data, your own data, aggregate it and send it up to your parent node in order to reach the gateway? That's the problem of data aggregation. Okay. Sometimes you may not be able to aggregate, you simply relay the data. In other cases, you can combine data from other nodes to with your node and compute a more processed version of the data and send it up. Okay. So that's a data aggregation problem. Now duty cycling problems become very important when you have networks of nodes. Now let's say you duty cycle each node to conserve battery. You put a 10% duty cycle, which is every minute they have to be up 6 seconds. Now if you can imagine that scenario, and you have a network of these nodes, and if they are using one another to route, if they are not all up at the same time, you cannot do routing. If node A wakes up for the first 6 seconds and node B randomly wakes up for some other 6 seconds, and then the other node is down, they cannot talk to one another. Okay? So you have to actually coordinate how they duty cycle. Okay? To coordinate the duty cycling, you have to do synchronization. We already talked about clock synchronization. They have to synchronize their clocks first, so that they can say, let's all wake up at the beginning of each minute. Now that our clocks are synchronized, we'll be up for the first 10 seconds. Okay? So all of these issues become important, because these are not always on nodes. You can't just simply assume that your neighbor is going to be up so you can communicate with the neighbor and have it forward data. So all of these issues which you don't really think of in a standard distributed system or even a network become important when you don't have always on nodes. And the nodes are very resource poor, that you have to duty cycle them or use other nodes because your radio is not powerful enough to directly talk to a gateway node and so on. Okay. So those are all design issues for the network itself. Now once the data reaches a gateway, then these are all powerful nodes, so you send it off to a server. And on the server side, you have to do a lot of interesting things as well. You have to do some analysis of the data to figure out what is the data telling you. Are there interesting events? What do the events tell you and so on. So this is the entire side problem of analytics. Okay, from analytics, you have to derive insights as to what the data tells you. You can make recommendations or exercise control. If the sensors allow you to actually control something in the environment, it's an application that allows you to do control, then you have to process it in real time and do some control. And many of these applications will involve not only data collection and analysis, but a control itself. Okay. So think of a self-driving car as an example of this. Okay. There are lots of these sensors on a self-driving car, cameras, all sorts of other sensors that are collecting data about the environment, road conditions, who's close by and so on. All of that data is going to be processed. And you have to exercise control on how the car is driving. Should you speed up? Should you turn? Should you stop? Because there's an obstacle. That has to be done in real time. Okay. There are many applications like this. We'll see an example of a smart building where you're going to collect data and decide when to turn the lights on and off, right? To turn the air conditioners on and off and so on. That's an example of data being analyzed and used to do control. You can also not just do control, but interact with the user, saying this is what the data is showing, here are things that the data reveals. So those are recommendations and things that we do. So both sides of the problem are interesting. Designing the network itself, and once the data has been collected, how to make use of that data to do something useful. Okay, how to process the data and do something useful. Okay. So that's a very quick background on sensor networks. What I will talk about now is green computing, and where I will focus specifically on energy issues in distributed systems, and then we'll put the two together. We'll do a case study of a system that is not only an example of a pervasive computing system, but also actually has a green computing background. So we'll do a case study that straddles both of these areas. So this is going to be a little bit switching of gears, but we'll put both of these things together. So what green computing is this new area that has emerged that focuses specifically on energy issues in systems. Okay. Now energy issues have been there for a very long time. Okay, so people have been looking at laptops and battery power and how to save energy for decades later. Okay. But they have become more important, and they are now more cross-cutting because of all of these trends I'm going to talk about on the next slide. Okay. So energy efficient mobile devices, long-standing problem. Now the recent growth of data centers has made energy efficiency for wired devices important as well. Okay. Simply because this data center have lots and lots of servers, and then aggregate they consume lots of energy. Okay. So saving on the energy bill becomes important. It's no longer a battery life problem. It is simply the cost of supplying energy to a very large computing system has become high enough that you want to make them more energy efficient. For mobile devices, you want to make them energy efficient so that their battery life is longer. For server class systems, you want to make it energy efficient so that your costs go down, your electricity bills go down. Okay? So different considerations, but both have energy efficiency implications. Okay? Now that is all work that is being done to that tries to make computing devices more energy efficient. More recently, what people have started looking at is energy usage of non-computing devices, okay, and how to make that more energy efficient. And we look at several examples, one being buildings as an example of an entity where you want to make energy efficiency a design consideration. Okay. So this whole area is referred to as applying greening to other systems, or what is called computing for greening. Okay. Green computing has two facets, which is greening of computing, which is how to make computing more energy efficient, and computing for greening, which is how to use intelligent algorithms and sensors and controls to make other systems more energy efficient. What we will focus on is basically this, because this is where the pervasive computing aspects come into play. Not that that's all about data centers and mobile devices and so on. Okay. Is that clear? The two facets of green computing. So I already mentioned some of the next 2 or 3 slides in the context of the data center lecture, but I'm just going to show that to you just to give you a flavor of these power issues in data center. So what this slide shows is how the cost of energy has been growing over the years for a typical data center, and all that you need to know, the curves are going up because energy is becoming more expensive, data centers are becoming more bigger and they consume more and more power. Okay? And there are more numbers I'll show you. So here is a back of the envelope calculation of energy bill of a Google's class data center, which actually assumes 100,000 servers. Okay, now that is already out of date. This is 3-year-old slide. Today most of these large data centers are up to million servers. They're much bigger. But let's take 100,000 servers, which is a fairly large data center. Okay? So each server consumes 500 watts typically. So the cost of a server, always on server, comes to $50 a month. Okay, you just take 10 cents per kilowatt hour electricity, you take multiply by the number of hours. That's how much electricity cost of a single server comes out to. Okay, now you can multiply that by 100,000. Okay? That gives you $5 million. That is just the server. Now you also have to cool these servers. So there's air conditioning infrastructures to cool the heat generated by the server. Typically that's going to be another 50 to 80% of the cost of running the server itself. So typically your bill may actually double because the air conditioner takes as much as your servers. Okay? So if you are actually incurring a bill that runs in millions of dollars a month, it is now in your own interest to make this computing infrastructure as efficient as possible. So your monthly costs go down. Okay? So that is probably a good reason why some of these issues have actually become very important, because companies are building all these larger and larger data centers. They are incurring big bills, and how to make it more efficient is actually an important problem. So what can you do? So there are many different techniques you can employ. One is you can somehow reduce the energy cost of the hardware itself, and we'll talk about that. Comes from efficient power management. It's a core operating system technique. We can see how to reduce the cooling cost of the server. That involves more mechanical engineering issues. We'll talk a little bit about that as well very quickly. And you can employ some good practices, which I'll also talk about. Okay. So how do you reduce server cost? You can basically, the essential idea is you have to manage your servers better. So there are two issues here. First is that servers are not what is referred to as energy proportional. I don't know if anybody has heard the word energy proportionality. Yes, no. It's an important concept in distributed server system. So this curve here, this is load power. So this curve shows you how typical power usage of a server varies as the load varies. Ideally, an ideal server would say if there's zero load, it shouldn't consume any power at all. Okay? But that's not how servers are built. The server is running even if nothing is happening on the server. CPU is on, the disk may be spinning and so on. So typically at zero load, a standard server can take up to 50 to 60% of its peak load. Okay? When the server is idle, it still consumes about 50% of whatever it consumes over peak. And then as the load increases, the power usage also goes up, because the CPU starts computing more, the disk starts spinning harder, there's more network communication, and this is at 100% utilization. This is the peak load. Okay, the peak load and peak power usage. So it sort of grows linearly. Okay, so what this is showing is that even if your server was idling, it would consume about half of its peak energy usage, and you're simply wasting that because nothing useful is happening on the server. Now the other side of the picture is most data center, if you look at the average utilization, is on the order of 20 to 30%. Okay, most of the data centers are heavily over provisioned. Okay, they have more capacity than they need for the average load. This is because the capacity is sized for the peak. Okay, most of the time you look at the worst case and what's the worst case load I incur, you buy that many servers, so you can always service the worst case demand. Okay, but on the average case demand may be significantly lower, which means the server is running at low utilization and it's consuming unnecessary power. because the server hardware is not perfectly power proportional. That's a hardware limitation. So putting all of that together, what that means is most of the time your servers are consuming a lot of energy and the energy is being wasted. Okay, because the servers may be idle and then you're just wasting all that energy, because if it's idle you shouldn't actually be consuming any power at all if your server was not designed. So you have to now use software level mechanisms to address this hardware level deficiency, which is you are not energy proportional. What can you do? You can actually use better power management. Simplest thing that most of the systems do is they turn off servers during periods of low utilization. So in the night you turn off a significant fraction of the servers, the remaining ones take on all the load in the system. During the day, as this load rises, you turn on more and more servers. Okay? This is intelligent cluster level power management. Okay? Some servers may be off, the others that are on will take over the load, and if the load increases, you turn on the servers. This makes it much better because you are packing the load that is coming into your system onto a small number of servers which are all running at high utilization because you packed it more, and you are using that power that is being consumed more intelligently. The other servers are off, which means they don't really consume any energy at all. Okay? This also makes the air conditioning more efficient, because if just idling servers still generate heat and you have to run the air conditioner at full capacity, you have to use less air conditioning as well. Okay? So you can use intelligent power management inside your data center on a cluster-wide basis by turning off servers. The basic idea is very simple. Turn off servers when the utilization is low. The virtualization team takes a big part here, because you can use virtual machine migrations to move applications of servers you want to turn off. Okay? So if there are 3 VMs and they are not doing much, you just move them to some other VM, pack them more tightly, turn the server off. Okay? So you can use virtualization techniques to achieve some of this power. So that's an important ongoing area of research, also of strong interest to any company that builds data centers, of how to do intelligent power management at a data center scale. Okay. So that's how you can address the server side energy cost. Okay. Other than making the hardware better, if you're stuck with the hardware, you have to use software techniques, which is in the OS. Now the other side of the picture is how do you reduce cooling cost. Right? Here also you can do lots of interesting optimization. Okay. So first is you can use your air conditioners better. So let's assume the air conditioners have zones which can be individually controlled. Okay, so basically each the region of the data center may be on its own zone. So this is showing you a heat map of what's inside the data center. These things are aisles, and blue areas are cool areas, and as you start seeing yellow and red, it means it's warmer. Okay? So you can do a variety of interesting things. So for instance, if you can consolidate all of the load to one part of the data center during regions of low load, this aisle will be red, it will be hot. All the other aisles is blue, so you turn off air conditioning there. Okay. So you are concentrating your air conditioning on only aisles that are warm. Okay, this is referred to as temperature aware workload consolidation. Okay, so you are basically reducing your cooling cost. If you have 2 servers on here, 2 here, 2 here, then they are all going to generate heat. You will need air conditioners everywhere. So by being smart about which servers, not only which servers, but where the servers are physically placed inside the facility, okay, you can actually reduce your air conditioning cost. If you just did the server, the technique I talked about on the previous slide, where you turn off half the servers, but if the servers are randomly distributed, then the air conditioner still has to run in all of the zones. But if you actually do this in a smart way, you will actually need less air conditioning. That's one way by which you can reduce some of the cooling costs. Right? Another technique that is actually used now by very state-of-the-art data centers is not use air conditioners at all. Okay? Use outside open air to cool. Okay? Rather than actually using an air conditioner to cool the data center, you can just take the hot air and blow it out and just intake the cold air from the outside. This works very well in most moderate or cooler climates. Okay, like North America, northern parts of the US, where the winters are cold and summers are relatively mild, you don't actually need to use air conditioners at all. You can actually use outside air to do. Similar thing, most of the time you can get by without an AC in your home. Okay, if you're in the south, this wouldn't work because it's much warmer. Okay. Now, there are many data centers that Facebook, Google run that don't use any actually. The reason you can do this is modern servers are engineered to actually operate at very high temperatures without having reliability problem. The most aggressive hardware that you can buy, you can run the server at 45 degrees Celsius, that's around 120 Fahrenheit, okay? And it will still run fine even at that temperature because it's engineered with that kind of reliability in mind. So many data center operators are taking advantage of it. They're saying the server has been designed to actually operate at that high temperature. Why am I spending all this money on my air conditioner to cool it and run the whole thing at 70 Fahrenheit when it can run at 120? Why not increase the temperature inside 200? If you run that inside 100, that means most of the time the outside air won't be 100 Fahrenheit. You can just bring outside air and cool your data center. So you see more of these technologies being used where you say natural cooling. Okay? Don't use, and then you can use the chillers mostly as a backup. Your air conditioners run only on the hottest days of the year when there's a heat wave or something like that. But most of the time of the year you don't use them at all. You do need ventilation. You can't just not use it, but with some ventilation and exhaust fans you can get by. Okay? Now this thing here is just an experiment that some researchers at Microsoft ran where they essentially put up a tent. They put some servers in that tent and basically just let the servers be. They didn't even close the tent. So if the servers are exposed to rain, humidity, winter climate, and still most of the servers actually ran without failing, which they did just to show that the servers are engineered with high levels of reliability by any reputable vendor, that you don't really need to use very high efficiency air conditioners or put them in very cold rooms and things like that. They can withstand ordinary ambient conditions. That were basically research experiments that were actually being done. Okay, so that's all I'm going to say about data centers. We'll now come back and talk about using computing to make other kinds of systems more energy efficient. This is going to be a case study on smart buildings. So we'll take buildings as an example of a pervasive system. Now you don't think of a building as a distributed system. Okay? But if you look at any modern office building, you will see that it has lots of sensors. Okay? There are sensors to monitor motion, there are sensors to monitor airflow, there are sensors that monitor air conditioning and so on. And these sensors produce data that is actually being processed and is used to exercise control. So there is computing in most of these buildings. If you look around, then you'll see there's a motion sensor there and so on. So there are these sensors, there is computing. So you can think of it as an example of a distributed pervasive systems where the sensors are actually being used to control the environment. And as I already mentioned, most of the devices you put into buildings are also becoming connected and smart in some shape or form. All your appliances are smart, your thermostat is smart. So you can now actually think of a building or your home as an example of a pervasive distributed system that has embedded intelligence and sensors. So we'll see what you can now do, what optimizations are possible, assuming such sensing, monitoring and control capabilities exist. Okay. So in other words, you want to use information technologies to make buildings smarter and greener. Greener meaning you want to reduce their energy footprint. So the example approach we will look at basically is what is called a sense, analyze, respond approach. So you are going to monitor, you are going to analyze, make predictions, and you are going to use the predictions to exercise control. And this is going to be a loop. Okay, so you control and you sense what's happening in the environment, you process, you take more actions as a result. Okay, so you basically be using this loop. All of the other words in the slide don't matter. What is important is to understand that this sense, analyze, respond or sense, analyze, control technique is an important one that's used in a wide class of systems, and that's the same one we'll assume is being used here. So we'll look at what can you do as far as monitoring is concerned in a building, and then we'll look at the analytics and controls. Okay, so as far as monitoring is concerned, there are many ways to monitor usage. Okay? There are many kinds of information you want to learn. First is you want to monitor what kind of energy is being used inside a building. Okay? You want to also monitor what is called occupancy data inside a building. Who is present in the building, what parts of the building are people present. Okay, because these are two key issues that you need to know before you can do something useful. If the building is completely unoccupied or there are entire floors or regions of floors that are unoccupied, you can turn off the lights there, you can turn down the air conditioning, you can turn off any devices that may be on and so on and so forth. So the two important metrics you want, not metric, but things you want to learn are what is referred to as occupancy and energy usage. Energy is not just electricity, it could be gas, water, all of these things come into play. I'm only going to talk about electricity here, but these ideas will apply to other types of energy a building may use. So what is shown on this slide is what is referred to as fine grain or outlet level monitoring. What this does is it gives you energy usage at the level of an electric outlet. You are trying to figure out what is plugged into each outlet and how much electricity that outlet is consuming. Okay? This is fine grain monitoring. Okay? This requires you to put energy monitoring sensors into each outlet. Okay? This is simply an example of a bulky outlet monitoring sensor. In this case, it's not integrated into the sensor. You plug it into the wall, and you plug in whatever device you want into the wall, and on that display it will show you how much energy is being used. You can put some sort of a wireless radio in there, it will transmit that usage somewhere. Okay? That's a device you can buy for $20 in any hardware store, okay, just as an example, but it does cost money. So this is one way you can monitor energy usage of a building. You monitor every electric switch and every outlet, and then you get a very fine grained usage of what's happening in every room, what's happening on every floor and so on. And this is fine grained monitoring. The other way to do it is what is referred to as coarse grain monitoring, where you monitor aggregates. You can monitor an entire building. Okay, in this case, this is actually a circuit breaker panel of a building or a home, and you actually put sensors into the circuit breaker panel, which shows you how much each circuit is consumed. Each circuit may feed lots of devices. You are monitoring the aggregate in this case. You are not monitoring each individual device or outlet. You are monitoring entire circuits and things like that. So you will now get, if you do this kind of monitoring, you will need an order of magnitude fewer sensors. You don't need one for every outlet or switch. You need one for every circuit or one for every floor or things like that. What is referred to as zones. This is coarse grain monitoring, much cheaper than going and replacing every outlet or putting expensive outlets in the environment. Okay, typically what is done is more coarse grain because it is fairly labor intensive to put lots of sensors everywhere. So there is some instrumentation, but most of the buildings will assume some level of coarse grain sensing. Okay, fine grain sensing is possible, but it's a lot more expensive. Questions?
So it's not for like the entire building, instead it would be like also for individual floors or things like that.
Yes, so if you're talking of office buildings, you will do this at floor level. If you're talking of a home, you can do it for an entire home, an apartment, because an apartment with just 3 rooms or something like that. So one sensor is good enough. But for an office building, let's say the CS building, that may be far too coarse grain. You can get data at that resolution, but it doesn't reveal a lot of information to you. It just tells you this building is consuming X, and you don't know what's happening inside. For that, you need a little more resolution, maybe at a floor level, for instance. Okay. So, what is shown there is actually a building level sensor, which is a smart meter. It's an electric meter. Just looks like a normal electric meter, but it has a capability to do more fine grain monitoring. It can monitor your usage at 1 minute granularity, and it has a wireless radio. It can transmit that to a server somewhere. Many electric utilities are now putting these smart meters onto homes. Okay, if your meter goes bad on your house, if it gets replaced, typically they'll put a smart meter which allows them to monitor your usage at a much more fine way. So rather than getting your electricity usage once a month to come and read the meter, they can get electricity usage, or you can also see what your electricity usage is once every few minutes resolution. So you can see graph of what is happening. Okay. That's a building level sensor. Okay, smart meter. The sensor is actually embedded in the electric meter itself. Now once you have collected this data, you have to, so that's actually the easy part in this case. Okay, the sensors, because this is electricity sensors, they don't need batteries. They're already plugged into the wall and so on. So a lot of those issues I talked about don't arise in this environment. But the more interesting issues come up when you have collected the data. What do you do with it? What what can you learn from it? So you can ask lots of interesting questions that allow you to derive some insight. So you can ask, does the home have an inefficient air conditioner? Okay. You can actually look at the usage of a building and ask, is the building consuming more than average for this size building? Is there something wrong? Is it inefficient in something? You can do this kind of analysis. There's an even more interesting analysis that allows you to take the aggregate usage and do what is referred to as disaggregation. Okay. Each appliance that you run in a home has a unique power signature. It has a certain way it consumes electricity. And you can look at that patterns showing up in the aggregate trace and you can disaggregate. So just by looking at that electric meter, you can figure out when your air conditioner is running or when you're using a microwave and things like that, because they cause sharp jumps in the electricity use, and the jumps correspond to the rating of the device, the power rating of the device and so on. So you can do disaggregation and figure out, do you have an inefficient washer or a dryer? Is your heating bill higher than average because you have a very old furnace that should typically be replaced and you will save hundreds of dollars on your heating bills every year? Yeah. So you can do this very smart statistical analysis of the these data, which use combination of machine learning and statistics to figure out answers to all of these questions. Okay. You can ask very simple questions of, is the building's air conditioning schedule correlated with the occupancy schedule? What that simply means is the air conditioner running when people are there in the building, or is it misaligned? This may sound very silly, but this is actually a very big source of energy inefficiency. Because what happens in most office buildings is the air conditioner schedule is actually decided statically by the physical plant guy somewhere. They assume people come in at 8:30, they leave at 5. Okay? And they'll set the air conditioner to actually, or the heater to come on at that time and go off at that time, or reduce the amount of cooling or heating after 5 or 6. Okay? Then nobody, once the schedule is set, nobody goes and checks, is that how people actually use a building? Okay? That's a very bad idea for a university building where there are students, because students may have different schedules than a 9 to 5 schedule. They may work late hours, they may come in on weekends, but you will find that the building is cold because they actually had misaligned the schedule. Okay, in this case it is undercooling or underheating, but the opposite may also be true. You may keep it running at, start it at 7:30, people trickle in at 9, so you have wasted 2 hours of using, of heating and cooling. Same kind of problem also occurs in a home. If you have a programmable thermostat that you program, you do the same thing. You program it to a certain schedule that says turn off at 9 because I leave for the department at 9, and turn on at 5 because I'm trying to come on at 5. That's a static schedule. So if your scheduled patterns change over time, either you will have to override, or you will see that you came home, the air conditioner had already turned on 2 hours ago because you had set the program to do that. So very simple optimization is to check the occupancy sensors for when people are home, check the air conditioning schedule or the heating schedules to see when the building is, the home is being heated or cooled, and align them better. Okay? Sounds like a very straightforward thing, but that itself can save 10-20% of your energy bill, because that's the amount of wastage you see in a typical building. These are misconfigured, okay, or misaligned. So that's the kind of analysis these sensors allow you to do. You can of course use renewable energy to make buildings greener, where you can put either turbines or wind turbines or solar panels on your roof to generate your own electricity. Okay. Now there are again interesting things you can do once you have renewable energy is, if you could predict how much energy you can get, you can use that energy. So because it's, once you deploy the solar panel or turbine, it's free for you. Okay. So there are techniques that will allow you to design, decide what amount of energy you will see tomorrow based on your weather forecast. If it's a sunny day, you will generate more solar energy. If it's a rainy day or a gloomy day like it's today, you won't generate much at all. Based on this kind of information, you can do interesting optimization. You say, I'm going to run my laundry tomorrow because there's a lot of free electricity. I don't think most people do that, but you can if you wanted to. You don't decide when to do laundry based on weather. But there are, if you have large solar plants, not a rooftop, These are the kinds of optimization utilities do. They do what is called sunny load scheduling, where they may say there's more power tomorrow, so I'm going to buy less from the generation guys because I am producing more of my own. And that way I don't pay them needlessly when I have to surplus electricity of my own that I'm generating for free. So that's using renewables. The last part about buildings is the human aspect. Unlike most computing systems where you can make decisions that impact only the computing system or the performance of the system, any decisions you make in the context of buildings actually impacts real users and humans. So considering the human factor in making this control or feedback decisions is very important, because if you decide aggressively to turn off heating before you left your house, you may start feeling cold. Okay, you're impacting user comfort. Users may complain saying, I don't like this smart thermostat because it's too smart. It's not doing the right thing for me. Okay? Or if you want the users, if you find that a user is wasting electricity because they never turn off lights in certain rooms when they are not in the room for long periods of time, how do you get the user to actually change their behavior? It's not an easy task because habits are hard to change. So this basically has a social aspect of what to do to incentivize users to be more energy efficient. If users are more energy efficient, the systems they use will also become more efficient because they will consume less energy, you waste less. So there is all these techniques people are using where you have phone applications that provide you feedback. They push an update to you. They push an update to you saying, remember to turn off your heater before you leave your house today because you forgot to do it yesterday. It will nudge you gently. Okay, maybe that will cause you to reduce your electricity usage. Or people are looking at designing, using social media to run competitions where a group of homes in a neighborhood. So this is an important area because it's not just the technology. You can design systems to be more intelligent and so on. But if the users that use them decide that they don't care or they don't want to participate in making the system more energy efficient, then you will only go so far. You can design a very efficient desktop, but if the user doesn't turn it off and they go away and it's running all night, it's still consuming electricity. Right? So we can only go so far without user participation. So this whole issue of how to get users to participate and actually enable the system to be more efficient is an important topic. And there are all sorts of things people are looking at: personalized recommendation, providing incentives, using social media to have peer pressure that encourages you to be more efficient and so on. And these are just some examples, applications where there are games that people have designed, there are applications that people have designed and so on. So this is, I think, somewhat different from a typical distributed system application where the user aspect is more key in achieving the overall goals of energy efficiency. It's not just the technology but the human aspect as well. Okay, so I think that's basically it as far as the case study is concerned. So quick wrap up, we are basically done. This is just a quick list of topics we have covered from the very first class through today. We started with distributed architectures. We talked about communication, RPCs, RMIs and so on. Spent quite a bit of time talking about processes and scheduling as the context in which we talked about virtualization, migration, distributed scheduling, things like that. Naming was so on. These are naming systems for distributed systems. Spent a fair bit of time talking about these canonical problems, all of the problems related to clock synchronization, logical clocks, leader election, distributed mutual exclusion and so on. It's an important area, or important topic, because these problems you encounter over and over again when you write large applications that are distributed. You come up with these issues over and over. So we just studied them in the abstract, but the thing to keep in mind is when you come up with the real system design, some of these ideas sort of come up there as well. You have to decide what techniques to use. And then we spent some time talking about replication, consistency and fault tolerance. We looked at what happens when data is replicated, how do you ensure consistency of the data? What happens if replicas fail? How do you ensure that you can detect those failures, recover from them? We talked about Byzantine's general problems, we talked about Paxos consistency and so on in that context. We spent some time talking about file systems and storage. We looked at a range of file systems. More recently, we spent a lecture and a half on security topics in distributed systems. And then we have done a whole slew of case studies. In distributed middleware, we looked at EJB, Store, Vajuni, so on. We've done case studies on streaming, the World Wide Web, cloud computing, and today's was on pervasive and green computing. So that's a significant breadth of topics. I hope that although we have covered them at some high level in many cases, that you got a flavor of what are the underlying design issues that underlie most of these distributed systems. And hopefully the lab exercises were also useful in understanding how these systems, how these techniques are actually implemented in practice. It was fairly straightforward labs, but they had some nuggets in there that hopefully you learned something from. So I can take questions if you have any, but that's really the end of the course. So we have just an exam left. If you decided to take an extension for your lab, you have a lab left as well. Okay. So turn those in. The exam is next week. Open book take-home exam, May 7th at 24 hours. And when the exam is done, the course will be actually officially done. Okay. So we'll end it here today. Hopefully it was a useful class, and if you have feedback, I appreciate hearing about it. You can come after the exam if you want to, or after the grade. It shouldn't be a problem.